This is an HP 35S programmable scientific calculator. In this video, I'm going to walk through some of its basic and advanced features, describe what I like and don't like about it, and compare it to some alternatives. Let's get started. So the first thing you might notice, like most HP calculators, this is not a standard infix notation calculator. It's a postfix or RPN calculator. There's no prominent equal key. If you want to add two numbers like 2 plus 3, you don't press 2 plus 3 and then equals. Instead, you press 2 and then enter to add it to the stack, and then 3. So now 3 is in the X register, 2 is in the Y register, and you can press the addition operator to add them together, the result being in the X register. If you want to multiply by 9, you can add 9 to the X register. That pushes the stack up, so 5 is now in the Y register, and you can multiply them. Divide in the same way. Some operators, like addition, subtraction, multiplication, division, as well as other operators like combinations and permutations, and so forth, require elements in both the X and Y registers. Whereas other operations, such as square root, just take what's in the X register. If we now wanted to square this number, we would have to actually use a shift key, here the blue or right shift key, in order to get x squared. There's a whole standard set of scientific functions. We can take pi, we can take pi divided by 4 and take the sign of that. We can verify that that's equal to 2 root 2 by multiplying by 2 and squaring it. Of course, there's some numerical precision going on here, and here we're looking at all the digits. If we say we can switch the stack, we can switch X and Y around. Maybe we want to go into degree mode, and we can do a standard calculator forensic test looking at numerical precision. We can take the sine, the cosine, the tangent, and then the arctangent, the arccosine, or the arc or inverse sine, and see whether we recover 9. We don't recover 9 exactly, but it's pretty close. This calculator can handle complex numbers very well, so we can enter 12 plus negative 16i very easily. If we just try square rooting it with the square root operator, we get this invalid data error. However, we can very easily just raise it to the 0.5 power, and that works just fine. Now, if we want to recover, say, the imaginary part of this number, this is not a built-in function. We can go and look in the integer part menu, and there's a whole bunch of functions here: sine, remainder, fractional part, integer part, but there's no real part and complex part. However, we can still do this. We can, for example, press enter again to stick this number in both the X and Y stack. We can take the argument, and we can take the sign of the argument, and then we can multiply that by the absolute value of the original number, and that can recover the imaginary part. Now, if we find ourselves doing that a lot, we can use a program to automate that series of keystrokes, and I've written a program just for that. We can execute a program that I've stored in label I, which will just take the imaginary part of a complex number. We can execute the program I've stored in label R to take the real part of a complex number. Let's go take a look at what that program is. Let's go take a look at, we'll go to I, and then we'll open up program mode. We can see the program's first instruction is to label it as I. Second instruction is to reduplicate what's in the X register into the Y register. Then we take the argument of what's in the X register, and then the sign of that. We swap the registers around. We take the absolute value of the original complex number, we multiply them together, and we return to interactive mode. This is why having a programmable calculator is so powerful. If this calculator is missing some function that you use all the time, no problem. You can easily program it into the calculator, or you can look on the internet where there's hundreds of programs people have written for this calculator. Many people, surveyors who use this calculator, are upset that it doesn't have an easy built-in way to do rectilinear to polar coordinate conversions and vice versa. But again, you can easily write a program for that. It does have other conversions that people might find very useful. There are unit conversions between degrees Fahrenheit and Celsius, pounds and kilograms, miles and kilometers, inches and centimeters. I find these to be really useful conversions, and you can even put them together in some ways. Let's say that we wanted to find the number of square meters in a 300 square foot apartment. So there's no direct conversion between square feet and square meters, but everything we need, we have here already. So we can first turn 300 square feet into square inches by multiplying that by 12 inches in a foot squared, so 144 square inches in a square foot. And then we can turn this from inches to centimeters, and again from square inches into square centimeters. And then if we want to turn this into square meters, we can divide this by 10,000, or 10 to the 4, because there's 100 centimeters in a meter. And there we go. We've gotten our conversion into square meters. This is something we wanted to do a lot. Maybe we want to just store the ratio between square meters and square feet. So we can store this ratio in a register, like say register P. And then in the future, we can just take our number of square feet, and we can recall register P, and we can multiply them together. If we didn't want to store it in a register, but wanted to write a program, we could go ahead and do that as well. And let's take a look at how we would do that. First, let's say we wanted to call this program P. We would go to P and make sure that it doesn't exist. Good. Now we go into program mode, and we can go ahead and start our program. So let's label our program to start with. So shift label, and we'll call it P. And then we will multiply whatever is in the stack by 144. We'll turn it into square centimeters, and then divide it by 10 to the 4, and then we'll just go ahead and return. Right? And so now, if we have our number of square feet in the X register, we can just execute program P, and we'll get our number of square meters back into the X register. Now, if we started from a totally blank stack here, let's go ahead and clear the stack and do that one more time. What we might see here is that we lose our original number of square feet. Maybe we want to have our program tell us that as well. Well, no problem. We can go and edit our program. So let's go to P, and then open up the program mode and edit it. And then we'll put in here, we'll just make sure that we enter this into the stack. So here, let's start with a clear stack again. 300, and then execute program P. And then sure enough, we're given a result back with 300 square feet in the Y register and 27.87 square meters in the X register. Programs can get a lot more complicated than simply repeating some keystrokes. You can have loops in programs, incrementing and decrementing loops. You can have tests, is X equal to Y, less than or equal to Y, and so forth. You can have random numbers and random seeds and so forth in programs. Programs can get hundreds of lines long, and can be used to automate common tasks or perform very complex functions. It's something that's really amazing about any programmable calculator, is that if the basis set is large enough, you can basically do anything you want, even if it's not built into the calculator. This calculator can store 27 programs in each of the lettered registers and one extra. You can store 26 36 variables in each of the lettered variables, which are separate, as well as about 2,000 indirect variables using these indirect addressing keys that can be numbers. The variables actually don't have to be just simple numbers. They can be complex numbers or even 3-element vectors. And so there's a lot of memory in this calculator. Each program can have up to 999 steps, and you can have branching and subroutines and so forth. There's some other neat features of this calculator, such as being able to enter equations in a kind of algebraic mode. And so this is something pretty unique for an HP calculator. You can enter an equation here. This equation is actually the integrand of the error function, the ERF function. It's e to the minus square root t times a constant factor. And with an equation like this, you can actually do integration, numerical integration. So if you wanted to know ERF of 0.75, you can set the limits of integration from 0 to 0.75. You can go ahead and choose this equation and then choose to integrate it and tell the calculator what variable you want to integrate it on. Now, this can actually be quite slow when you have a lot of precision. And you set the precision by the number of digits that you're showing. So this is going to go on for quite a while, so I might just actually stop it here. And let's just change the precision to say 4 significant digits, and then let's go ahead and do our integration again. And now you see it takes maybe 4 or 5 seconds to get the answer. And that might be a little bit long, so maybe you want to do something else. Maybe you want to, for example, put in a polynomial approximation to the error function, and that's what I've done here. It's quite long. I got this polynomial approximation from Abramowitz and Stegen, the famous handbook for mathematical functions, but only have to enter it once. And so let's go ahead and evaluate this equation. So we're going to run this equation. And we have to give it our x value. And there we go. It computes E for us, or for us. I've also put this in as a RPN program, so we could just execute program E, and it will go ahead and compute this polynomial approximation as well. There are lots of different ways to do things in this calculator. If we wanted to, say, solve the roots of an equation, we could go ahead and do that. Let's add a new equation here. So let's say we wanted to solve the root of 1 times the square of x plus x plus 12 equals 0. This is a standard quadratic equation. And let's go ahead and solve this. And we tell it what variable we want to solve for. And I'll go ahead and solve, and I'll find the first root. It thinks the first root is 4. Of course, there's 2 roots to this, so we can give it a different initial guess. Let's say we want to give it a guess of minus 2. We can just go ahead and store that as our initial guess for x. And let's go and try to solve this equation again. And sure enough, we recover the other root, minus 3. This calculator can also be very useful in the workshop if you work in fractions. You can do something like add 3 and 3 30-seconds and 6 6/64ths and add them together. You can do operations on them. If you want to convert this number of inches to centimeters, you can do so, and then you can pop out of fraction mode to get your decimals back. There's some other features of this calculator I find very useful, in particular statistical functions. So let's go ahead and make sure that we've cleared our statistical registers for a moment. Let's say that we were grading an exam and we had some students. One got a 90 on the exam, one got an 85, one got a 95, one got an 86, and the last one got a 91. So now we've added 5 different list of 5 elements into our statistical registers. We can go see the sum of all of them, but what we really might want to know is the mean. So the mean here is an 89.4, and we can check the standard deviation as well, and the standard deviation is 3.6. There's something else we can do with the statistical registers, which is to add XY data and do linear regression on it. And so in adding XY data, just remember that this is the X register and this is the Y register. So if we wanted to, look at maybe speed of something, and we have its position with respect to time, maybe its position at time 1 is 10, and we can add that, and at time 2 is 19, we can add that, at time 3 is 31, we can add that, and at time, let's go ahead and say at time 6 is 64. All right, so now maybe we want to know where it's going to be at time 17. So we can do a few things. We can go into this linear regression, and we can see what is the expected y value at the x value of 17. We can see what the correlation coefficient is, how good does this fit with a linear fit, and we can see what the slope of the line is, almost 11, and we can see what the y-intercept is. This is the standard y equals mx plus b formulation here. I find this to be very useful in order to do very quick linear regression. So there are some other functions of the calculator, but I would say this is a good introduction to a wide variety of things you can do with this calculator. What do I dislike about it? Are there some nits? Yeah, there are a few. Pretty minor overall, I would say. Probably the biggest two things that I dislike about the calculator are the way that it doesn't show the thousand separator until after you've entered a number. Okay. Notice that the thousand separator shows up here. In fact, you can decide whether you want a thousand separator or not. You can decide what you want for the radix symbol. But unlike some other calculators, it doesn't show you the thousand separator as you're typing in digits, which is when you can backspace and correct an error. And so I find that to be a real nit. And there's something else that I find a little bit annoying. So if you have, say we put the calculator into all again. So this is quite nice. It doesn't show any extra decimals as you're working. But if you have a very large number, say 45 to the 9th power, the exponent is way off on the other end of the screen. You have to use the arrow key to go back and see it. And that really seems like a shame. So I find myself often working in fix 9 or fix 4 or fix 2 instead of all. But of course, in this mode, when you have simple numbers like that, you have a lot of extra decimals. And so to me, those are the two things that bother me the most on a daily basis. There's some other things, I wish that the store key wasn't in a shifted position because you use that a lot. I'm always a little bit confused that the XY key and the roll down key to roll up and down the stack are way out here instead of being right next to the enter key where I expect them to be. In fact, I don't even think the roll down needs its own key because we have these nice arrow keys here that don't really do anything useful in the interactive mode. And so I always think that these should be the stack roll up and roll down keys, and then we could use this key for something else. But I would say that that's pretty much it. As far as nits, battery life could be a little better. You typically get 6 to 8 months out of a single battery, single set of batteries. They're wired in parallel on purpose, so when you replace them, if you replace one at a time, CR2032 cells, you won't lose your stored programs. There is no I/O for saving programs or inputting programs other than the keys. I don't find that to be a real problem, and I think that major use of the calculator is in professional exams for engineers and surveyors, where calculators with I/O are not permitted. But I actually don't find it such a big deal to remember to write down your programs. It's not so bad to type them in. It's actually good that you learn how a program works by typing it in. There is supposed to be a checksum feature to make sure that you've typed in a program exactly, but unfortunately that just doesn't work at all in this calculator. And so that's probably the only real bug actually in the calculator. There are a few other programmable scientific calculators that are available used. That have a similar set of features, most notably the HP42S, the HP15C, and the WP34S. I'm going to say right out, I actually prefer this HP35S to all of those alternatives. The HP42S is a very popular calculator, which is now very expensive because it hasn't been made in a while. It has roughly the same set of features as the HP35S. It has built-in matrix features, which the HP35S does not, although there's a program you can input that gives it a bunch of matrix features, and there are inbuilt system of linear equation solving here. But I actually prefer the key feel and the appearance of the HP35S. You can download a free HP42S emulator for your smartphone from Thomas Oken's excellent free 42 program and give it a try. The HP42S has a philosophy of a simple keyboard with a lot of menus and a lot of different modes, and I actually much prefer this sort of more both classic appearance and more classic behavior of the HP35S in having almost everything accessible directly on the keypad, with only a few features actually, leading to modes and menus. There's the HP15C, which is part of the famous Voyager line of HP calculators. I don't own a 15C, but I do own a 12C, which is actually still made. Physically, it's just terrific. It has probably the best LCD display I've ever seen. It has an even better key feel and build, and it used a very innovative silicon on sapphire design so that the batteries, instead of lasting 8 months like these batteries, will last 8 to 10 years. I have to say, though, that I find the landscape orientation of the 15C to be strange. I find it just much harder to use than the 35S. When I first got the 35S, I basically sat down and I read the paper manual from cover to cover, and then, I pretty much got it. And every once in a while, I have to go back and look up how to do something, like how to format the increment loop counter or something. But I find it's really quite easy to use, whereas the 15C requires a lot of memorization to do things like use matrices and so forth. And so I find the 15C to be it's not as great a user in everyday life, and of course it only has a one-line LCD display rather than the two-line display of the 35S and the 42S. The WP34S is very interesting. It's actually a HP30B business calculator that's been flashed with a custom software to turn it into a programmable scientific calculator. On the one hand, it's much newer hardware. It runs probably hundreds of times faster than the HP 35S and also has a lot of memory. The key feel is honestly not as good as the HP 35S. It's also very confusing because it has just an unbelievably large number of functions built in. And so again, there's good and bad aspects to that. It has a sort of 1.5 line display. It has really a one-line display with a few extra pixels on top that you can put some explanation in. I actually own a WP31S, which is a non-programmable little brother of the 34S. It's in my office right now, and I can't get there because of the coronavirus. But I use that calculator as well. It's nice that it has just such a large number of functions built in. But I think for the sort of novice, the intermediate, the typical user, the 35S is a better machine than the 34S, which has a very steep learning curve. To me, I honestly don't even look at other manufacturers' calculators because I'm just so used to using RPN, and I think it's just such a better way to do computation. And so I know that there are other programmable scientific calculators available, but they're not RPN, and so I honestly don't even consider them. There are, of course, HP graphing calculators available. Those are much larger, more complicated, and I find that it's just it's not really what I'm looking to use in a sort of daily basis. I feel like for the kinds of things that I might use a graphing calculator for, I'm probably better off firing up Mathematica on a computer. But as a researcher, an engineer, a scientist, an entrepreneur, we calculate on a daily basis. And I think we really deserve a machine that's optimized for calculation. And so for me, that is the HP 35S Scientific Programmable Calculator. Thanks for watching.